Welcome to the EC online game changer seminar, Captivating Cosmology from the Big Bang to Tomorrow. I am very happy to have today Mustafa Amin from the Rice University in Houston, Texas. So just very briefly about EC, we started this online game changer seminar series now 2 years ago. And it was actually so successful that we decided to introduce always new series. And recently we started with the series on cosmology, this with the title, Captivating Cosmology from the Big Bang to Tomorrow. And this is a series of 10 talks. Today we have Mustafa Amin, and he will talk about inflation ends, what's next, a story of how the hot Big Bang began. So I will just give a very short introduction about Mustafa itself. So Mustafa is an associate professor of physics and astronomy at the Rice University in Houston, Texas. Before joining Rice 7 years ago, Amin held the Senior Kavli Fellowship at the University of Cambridge and the Pappalardo Fellowship at MIT. Then he obtained his PhD from Stanford University and undergraduate degree from the University of Texas at Arlington. And he's working on cosmology, how did inflation end, and the hot Big Bang began. And he has published more than 50 peer-reviewed articles. And his work is currently supported by NASA and the US Department of Energy. And myself, I am Maurizio Falanga, Director in Astronomy and Astrophysics here at EC. And just the last information, how you can ask them questions. So we will listen now to Mustafa around 40-45 minutes. And afterwards, the audience has two possibilities in asking questions. One is raising your hand and you will be unmuted, or write your question directly in the chat also during the talk, and then we will read the questions at the end. And just before you even start, I would like to thank already Alessandra Conversi about the really excellent your seminar series is. So thank you, Alexandra, and let's listen to Mustafa.
All right, thanks a lot, Maurizio. It's a pleasure to be here, at least virtually. I've looked at the talks in the series and they're all exciting, and I hope I can live up to what all the other speakers have already, the great job that all the other speakers have done and the speakers to come. Okay, so my plan today is to tell you a little bit about what happens at the end of inflation and how the hot Big Bang begins. But before we get into this, let me start with a brief survey, which I'm not going to actually conduct a survey, but I want you to think about the answer to this question. When I say, what is the Big Bang? What is it that you think it is, right? Is it one, the initial singularity when space-time itself came into existence? Or is it a period of early, rapid, accelerated expansion, often called inflation? Or three, do you think of the Big Bang as a hot, dense, rapidly expanding state of the universe at very early times? And perhaps if some of you are listening from the US side of things, perhaps you think about it as the TV show, Hot Big Bang. So I want you to just think about this for a moment, because as we go on, it will become important about which part of the story is the thing that we have most evidence for and which part is most speculative. Okay, so with that, let's now talk about the end of inflation and the Big Bang. But to do this, to really talk about the end of inflation and the Big Bang, I want to put it in the context of our cosmic history. Our cosmic history perhaps ranges from 10 to the minus 44 seconds all the way to about 14 billion years. It's a huge period, and these little ovals that I'm showing you are eras from which we have some observational information. let's begin at the beginning. And here, the beginning time I'm writing down here is about 10 to the minus 44 seconds. This is about the Planck time. And I don't have that much to say about this period. Why? Because around this time, it's really hard to even talk about space-time as some classical thing, or even time being well-defined is not true. So it's hard to talk about this period. So we'll just move forward and say, okay, we don't know what's going on there and at the moment. Moving forward a little bit, cosmologists currently think that the universe underwent a period of expansion, which perhaps lasted for about 10 to the minus 36 seconds. And this period of expansion is an incredible thing that happens. Okay? The universe expands by a factor of about 10 to the 26. What I mean by this is that the relative separation between points changes by a factor of 10 to the 26. This period, as being demonstrated here by one of the inventors, or Alan Guth, is a period where the universe expands by this amount. And it's very useful because it allows us to explain why the universe looks the same in different directions. And at the same time, and perhaps even more importantly, it also allows us to generate initial fluctuations that eventually give rise to galaxies and ultimately us. So this is this period that lasts for about 10 to the minus 36 seconds. The universe grows by, or the relative separation grows by a factor of 10 to the 26. This 10 to the 26 number, at least for me, is pretty hard to imagine. So one way of thinking about what this 10 to the 26 is the ratio of the size of our galaxy to the size of a flu virus. That's how big this number is. Okay, so what's next? So we've got inflation. Next, we'll wait for a bit and allow the universe to evolve for about a second. Okay, so remember, we are going from 10 to the minus 36 second all the way to a second. And this is a time where the first light nuclei, helium and so on, start forming. This period is something that we have pretty good direct observational evidence in the sense that we can predict what the amount of helium to hydrogen should be. The ratio of helium to hydrogen should be about a factor of 1/4. We can predict this and we can compare it with observations, and this turns out to be the agreement seems to be quite good. So this is what's happening at about, and the plot on the right is giving you a sense of some of the abundances of light nuclei. Helium, a bit about helium-3, helium-4, a bit about lithium, and so on. Next, in our cosmic history, we wait for about 400,000 years. So we already have formed nuclei at about a second after the Big Bang. Now, 400,000 years later, we are forming the first atoms. The first hydrogen atoms are coming into being. This period, in fact, we have exquisite information about. We can look at the sky today, and we can see light from the time that the first atoms formed. This splotchy picture with red and blue dots is a picture of the light that's coming from that time, false color image. And the graph that you see is a Fourier transform of this image. The thing to notice is that the data points on there, these blue dots, fit theory, which is a red curve, exceptionally well. So this period, about the time when the first atoms formed, we know really well, and this data I'm showing you is from the Planck settlement. Many decades ago, Lev Landau used to quip that cosmologists are often wrong, but never in doubt. But this data set, this cosmic microwave background data set, in my opinion, has changed that, right? Now we can get percent level information on parameters on our models. So this is when the first atoms, right? Moving forward. After this period, we'll talk a bit more, but let me come back to this question, this survey that I initially put up, right? Like, what do we think of as the Big Bang? So hopefully, even in this short presentation, you can get the sense that we know very little about the initial singularity when space-time came into existence. We can say very little about that. We don't have much confidence in, we have ideas, but not much detail about what's going on there. Inflation, because it sets up initial conditions and it has implications for what we see in the sky, we have some understanding of, but still not a complete theory or detailed understanding of. However, then thinking about a hot, dense state of the universe filled with particles, at least from the time of the first nuclei onwards, I think we have direct observational evidence and strong confidence that the universe was in this state at some point. So when, at least as cosmologists, when I usually say the hot Big Bang happened, I'm thinking about the third period with a significant amount of confidence. I can say that, yes, this is fine. The other things are a little bit more speculative. All right. Moving on. So we've had our first atoms. What happens next? So next, gravity now becomes the dominant thing that determines how the universe is behaving. Gravity starts collecting dense regions and making it more dense. Less dense regions get more evacuated. The rich get richer, the poor get poorer. That's what gravity does. And eventually, if you zoom in to some region of a small region of the universe, you'll start seeing the formation of galaxies, gas falling in, and a galaxy like us forms somewhere in the universe. And within this galaxy, we have stars, and of course, around a star like our sun, we are sitting as a third rock. And on this third rock, as of the past few thousand years, we are looking back and thinking about this cosmic history. So this is sort of the big picture of what our cosmic history has been, right? Right from inflation all the way till today. But if you notice, I sort of skipped a big chunk of it in the middle. I skipped from 10 to the minus 36 second onwards all the way to a second, and I didn't say anything about that. You might ask, okay, so sure, there is a gap in our cosmic history that I didn't talk about, but does it really matter? In the 14 billion years of history, do we care about this 1 second that I didn't talk about? Why should it matter? I want to convince you that this part is really exciting and really does matter. To get a sense of why this early period matters, let me give you some sense of what's going on. So you can connect with these little handy formulas that I've written down. You can connect the time, the cosmic time, that is what time it is in the universe since, say, after inflation, to what temperature it is there. That's the first formula on the top. The second formula tells you how the density in the universe is connected to time. If you now think of, if time changes from 10 to the minus 36 seconds to 1 second, your temperature will have changed by, if I think correctly, it's about a factor of 10 to the 28. So there's a huge change in temperature when the universe goes from 10 to the minus 36 seconds to 1 second, even though it's only a second in the universe's cosmic history. Similarly, the density also changes by a humongous amount during this period. Now, why does this matter? Because our understanding is that physics, the type of physics that's effective, that's operating, changes rapidly as you change the characteristic energy scales in the universe, or the characteristic densities. And because the density and temperature is changing so much within this 1 second, it tells us that a lot of things must be going on during this period. Let me give you sort of a quick sense of what kinds of things should be going on. Even though I said that this period is, blank and we know nothing about it, it's not that it's completely blank. We have good ideas about what should have happened during this period. We just don't have direct access observationally to what's going on. We have some indirect information about what's going on because we can create some of these conditions in the early universe by looking at our particle accelerators, like the Large Hadron Collider. That gets us to about, in particle physics units, a few tera electron volts. However, this is not really getting us all the way till the end of inflation, which could be as high as 10 to the 16 gigaelectron volts. So in this, if you're trying to think what kinds of things happen during this gap, the things that happen include things like inflation must end. We must populate the universe with particles that you and I and everything else is made up of. The difference between matter and antimatter, the slight should arise perhaps during this period. Dark matter, which dominates the mass density of the universe today, should come around during this period. The separation of forces, or thinking about how fundamental particles getting mass through the Higgs mechanism, happens during this period. Also, quarks, which at some early stage were free, get confined together into hadrons during this period. So this gives you a sense that a lot of things are happening within this gap. So it's an exciting period in our cosmic history. If you want to think in terms of how human beings have accessed different energy scales, the graph on the right is telling you a little bit about, atomic scales are about 10 to the minus 9 GeV, which is roughly 1 electron volt scale. Nucleus scales are, MeV, mega electron volt scales, that's 10 to the minus 6 GeV. High energy scales like that book by the LHC are 10 to the minus 3 giga electron volts, or a TeV. Sorry, that's not quite right. It should be 10 to the 3 electron volts, not 10 to the minus 3 giga electron volts. And then we have this gap, even after using the LHC, we have this gap all the way to inflation that we don't know what's going on. By the way, if you are interested in learning about this first second or so, I think the excellent book, it's a classic by Steven Weinberg, who unfortunately has passed away. It's an excellent book on learning more about what happened in this first second. I should also say that first second onwards, you also learn from Julian in his talk, if you haven't seen it, from a week or so ago, where he talked about what is happening at the first second when neutrinos are produced. It's one of the things I will not talk about because he has done such an excellent job of telling us what happens at that time. Okay, so hopefully this convinces you that this gap, even though we don't have direct observational information, is exciting, and there's a lot happening here. In the time I have today, I obviously can't tell you everything about what's taking place during this time. So I'll have to focus on one or two things during this period and go into a little bit more detail about that. So what I've chosen to focus on is what happens right at the end of inflation. So right at the beginning of this period where we don't know much about what's going on. So it's the highest energy scale that after inflation that we might have, and we want to see what's going on at that period. What do we know? Or what have we learned so far about it? What is the current state of the art? Just a reminder. So remember, there is a period I've already mentioned early on that the universe expands by a humongous amount. And it's accelerated expansion, which means what it means is that the separation between points in space, if I characterize it, say this is my pen has some. Okay, there we go. Give me one moment. Let's see. So if the separation is, let's start this again. So inflation this period of rapid expansion that we've mentioned. Now, an important part about this is that it's not just a rapid expansion. It turns out that to do its job, meaning to make the universe appear the same in different parts, as well as produce the seeds that give rise to structure in the late universe, the way the universe must expand during this period should be such that if, say, the relative initial separation is delta x, and the separation sometime later is some function of time times the initial separation, where a of t is often called the scale factor, then this expansion has to be such that it is accelerated expansion. That is, not only is it expanding, but the speed at which the points are being separated is also increasing. And this is important for inflation. Now, this type of expansion has implications. Einstein and Friedman have taught us that the way the universe expands relies on the contents that it has. So for inflation to expand in the way it does, that is for the relative separation between points to expand, to move away from each other in an accelerated fashion, it would require that what the contents of the universe at this time, their energy density must remain constant. This seems quite counterintuitive, right? So space is expanding really in an accelerated fashion, and yet the energy density is remaining constant, but this is what Einstein's theory requires, that for accelerated expansion, you need the energy density to be constant. This is not so different if you've heard about it, about how dark energy operates in today's universe. This is happening in the early universe. So during inflation, universe expands and it's undergoing accelerated expansion, and the energy density is remaining constant. This is the energy density of the inflaton, that is the thing that's causing this accelerated expansion. But what about the energy density of the other contents at that time? Let's say you had some photons or radiation during this inflationary period. Well, that energy density doesn't have this property that it remains constant. Space is expanding, and this energy density gets significantly diluted. Space is expanding by 10 to the 26, so all of the energy density of radiation and other matter gets diluted away. So you end up just with a universe filled with just the thing responsible for inflation, which is the inflaton energy density, and nothing else. So inflation is great because it makes the universe appear the same in all directions and causes and gives us the seeds for formation of structure, but it also leaves the universe cold and empty, just filled with the inflaton itself. So this is now a problem, right? So how do you go from inflation to a universe that we know observationally is filled with matter and radiation, and it's a hot thermal soup? So it is this transition from inflation to a hot thermal soup which goes by the name of reheating. And this is what needs to happen at the end of inflation. That is, inflation must end and populate the universe. This period, this reheating period, is currently a very active area of research. Okay? The questions we are trying to ask in this period is, how did inflation end? Okay? How did this accelerated expansion that was going on shut itself off? How did that take place? And then, how is this energy density that's present in the inflaton responsible for this accelerated expansion? How did that get converted eventually into standard model particles? That is, how is the inflaton coupled eventually to standard model particles? So these answers, in some ways, we don't know. We have ideas of how it could be, but we don't know in detail how this is taking place. This is sort of a situation, I would say, that it's not that we don't have any models. We have models we can write down. It's just that we don't know which one is the correct one because we don't have enough information to distinguish one model from the other at the moment. But I'll tell you some ideas on how we might go about trying to do this. So as I said, this period is, active area of research and and because we don't know exactly a unique way of getting from this inflationary period to the hot thermal state, There are many ideas out there. And the phenomenology of what happens in between can be complex. I'm not going to go through this entire slide, but a few of the things that can take place in going from the inflaton-dominated universe to the radiation-dominated universe could be, a slow decay of the inflaton into particles that we know and love. There could be a violent decay going from one to the other. You could generate relics in this period. Lots of things could go on in this period. And we need to, because we don't know what's going on, we need to explore these possibilities and look for implications. Something that I spend a lot of time on is what happens if the transfer of energy from the inflaton, both the end of inflation and the transfer of energy, is not some slow, gentle process, but it's a violent process that happens very rapidly. What kind of things would happen in that because of that? So let me just, in this slide, give you some, hopefully you can see the videos running, and it shows you actual numerical simulations of what could be happening in the universe during this early phase. These boxes that you are seeing are really small scale regions of the universe at early times. Okay, so they're in some sense, these are smaller than the size of an atom, the boxes that you are seeing. The colors and dense you are seeing basically represent what density is doing at that time. So it starts out as roughly homogeneous, but because of this violent end of inflation and rapid transfer of energy, the density in the universe fragments from this homogeneous inflaton state to something much more turbulent and active. The first box that you see is about what is happening with the violent transfer of energy. These blobby structures are something I'm really fascinated by. They're called solitons. These are compact objects that can form at that time in some cases. The blue stringy stuff is another kind of objects that can form during this transition at that time. There could also be phase transitions between different states that take place. All of these phenomena can take place within that, right at the end of inflation. And as I said, because these phenomena are complex, you can't necessarily work these out by pencil and paper. And these things, as you are seeing, done by me and my collaborators, these basically are solving a complicated set of partial differential equations involving different fields on a computer. Okay, so these are the exciting things that can happen at that time. And over the past few decades, as computers have gotten powerful, and we have learned more about what kinds of models we should be considering, a lot of progress has been made in exploring these possibilities at that time. But ultimately, how do we know what has taken place? We can do these calculations in detail, and that's important, and we can make predictions. But of course, we have to look at observations in the sky today to look back and say, okay, can we say something about what had happened at that time? So to do that, we rely on what are called relics from this period. And such relics could include things like gravitational waves. These violent events taking place at that time can churn up space-time and produce ripples in them. And those generate gravitational waves that we can hope to detect today. These huge churning up of densities at that time can also lead to formation of tiny black holes at that time called primordial black holes. Those either themselves or they can seed later black holes, and those can perhaps survive till today. You, of course, can also generate extra radiation. We'll talk about this in a moment at that time that can survive till today and bring us information from that period. A slightly less intuitive thing is that these dynamics can also influence the way in which the universe expands after inflation. And this has an indirect effect on what we see in the light coming from the time of the first atoms. So all of these things can bring us, these relics, which we can look at in the sky today, can bring us information about this very early period right at the end of inflation. So let's focus, just to be a little bit more technical, when we try to get information about what happened during inflation, we can get that information by looking at this patterns of temperature in the light from the time of the first atoms. Because of that accelerated expansion, you can see effects of this early period here. However, exactly how these effects map depend upon how the universe expanded during this period. And that relies on what is going on in the universe at that time. So my collaborators and I have been working on figuring out, what are the possible ways in which the universe can expand during this period? And can we use that to determine something about what's going on during this period by looking at the cosmic microwave background, given a model of what happens during inflation? This plot here is a standard plot that's a technical one, but it tells us something about inflation. And these dumbbells that you see here are meant to characterize the uncertainty in the model, because we don't know what's happening about how the universe is expanding between the end of inflation and the CMB. But if we know better about what's going on at that time using the types of simulations that I've shown, then we can reduce this uncertainty significantly and learn more about inflation itself. Or given a model of inflation, we could learn something about what happened during this period. I also told you that the violent dynamics that happens during this period right here, say described by this, this tiny box that we've simulated, has been simulated, these violent dynamics churn up space-time and lead to the production of ripples from that time that can be detected today. There's something really great about gravitational waves and something very terrible about gravitational waves. Unlike light, gravitational waves interact so weakly that once produced, they almost come towards us unimpeded, bringing us perfect information about what's happening at that time. So all the way from here, if you're able to detect them, they would bring us information. Light, on the other hand, because it interacts strongly, only can bring us information from somewhere here, from the time that the first atoms formed. So gravitational waves would be great for getting information, but of course, it's also difficult because gravitational waves, because they interact so weakly, are also very hard to detect. We've detected gravitational waves from astrophysical sources, but we haven't detected them from primordial sources like this. I think Will gave a talk about 2 weeks ago where he talked about gravitational waves from inflation. The ones I'm talking about are ones that are produced after inflation from this violent transfer of energy, or how inflation ends. This seems like a great thing to do, but there are caveats. One is because this reheating is happening so early in the universe and it happens after accelerated expansion has ended, the frequency of these gravitational waves today tends to be very high. So typically the frequency of the gravitational waves from this reheating like things will be between a megahertz to a gigahertz. This is a very high frequency because things like LIGO, which you might be aware of, which detected gravitational waves recently, is at about a kilohertz. So this is somewhat far from that regime. So in addition, because this process happens so early in the universe, and because because of the expansion of the universe, the amplitude of the waves is also going down as it gets to us, the amplitude of these gravitational waves is also very, very small. It's many orders of magnitude away from any current detector technology that we have. So while this would be a great probe, I think currently this is still something for the future to think about. And I think the time is right to think about new ideas of how we could potentially detect this primordial signature. Again, let me stress, this is different from that from inflation, which can be detected in the CMB. This is more about what happens after inflation, and this is the high frequency radiation. And again, I can say a lot more about this if you're interested. But this is something that's an exciting thing to hopefully detect in the future, but it's a tough problem. There is another way, though, around instead of detecting these gravitational waves directly, that is by building detectors, and we can see the squishing and stretching of space-time by a detector, we can go for something different, which is what is the total amount of energy density in gravitational waves. It turns out that the cosmic microwave background can provide exquisite information about any species, extra species of radiation beyond what we know in the standard model. We already know about neutrinos, we already know about photons or light particles. The cosmic microwave background, or the light from the time of first atoms, also contains can tell us if there is any extra species. I'm sure Julian, when he talked about neutrinos, has already told you a bit about, if you've seen the talk, about effective number of neutrino species. If not, it's just a measure if there's extra amount of radiation around there than what we expect. And that can be detected with current and especially with future generation experiments like CMBS4 to sub-percent level. We can look at the deviation from what is expected at sub-percent level. And that tells us then that if we see a deviation, or if we don't see a deviation from the expected one, then that constrains the amount of gravitational waves you could have generated during this period. And that in turn gives us information about how violent this energy transfer could have been at that time. So these are all coming up, and there are exciting things to put limits on this period that we know so little about. I believe CMBS4 is set to be construction soon, and 2029 we should update it. These are a collection, by the CMBS4 is a collection of telescopes, both at the South Pole and that. Okay, we're almost getting towards the end. So let me sort of tell you quickly in a couple of slides something else. It's a bit of an aside from what we have said, but I hope you'll find it interesting as well. So I've told you all about the end of inflation and the hot Big Bang as a process by which you transfer the energy from a cold inflaton to a hot thermal soup of particles. So it's a particle production mechanism at that time. Something else that this process does, is it generates a lot of entropy. So entropy is it's a measure of how many different ways can you arrange a system and get the same final macroscopic observable, say that like the temperature or pressure and something. Now the inflaton is just a cold single state. It doesn't have that much entropy. However, when you think about the hot thermal soup of particles, you can rearrange the particles in many different ways and still get the same hot thermal soup. So that hot thermal soup is a very high entropy state, whereas inflation was a low entropy state. So you can also think of this going from inflation to hot thermal soup as an entropy generating process. And if you take, roughly think about what entropy is there in the universe we can see, then it's this entropy that you've produced at that time is in units of Boltzmann constant KB, is this very large number 10 to the 89. This is the entropy of the observer. And most of this entropy ends up being held by photons or relativistic species that are produced at that time. If you actually track this entropy that was produced at that time, the total entropy in some patch of the universe, and you follow that patch to the observable size today, then you'll find that the total entropy, at least and I'll mention the caveat in a moment, the total entropy in the particles that were produced is basically conserved. It doesn't really change. Sure, it's not exact, but it's more or less, it's conserved from then to now. But so the entropy produced during the early universe at reheating is basically the entropy we have in the particles today. And most of this entropy is carried by the photons in the CMB and neutrinos. However, in reality, the entropy of today's universe is not quite this. It's a little bit, not a little bit, it's a lot bigger. It actually it's about 10 to the 104 instead of 10 to the 89. And all of this entropy, extra entropy, is not in the particles. It's actually locked up in black holes. So black holes themselves carry a huge amount of entropy. They are the more maximally entropic states of systems. So when black holes form, the entropy of the universe, in some sense, those are the things that lock up most of the entropy. As a fun number to think about, the entropy in the black hole, supermassive black hole at the center of our galaxy is comparable to the entropy of all the CMB photons in the observable universe. So it's a pretty large, black holes have a lot of entropy. But again, this is a bit of an aside, but at least hopefully you keep in mind that reheating was an entropy generating mechanism, and most of the entropy in particles apart from black holes was generated at that time. All right. So let me summarize. Hopefully I have given you a flavor of what happens at the end of inflation and how you go from a period of accelerated expansion, which is cold and devoid of particles that you and I are made up of, into a hot thermal state. It goes from a low entropy state to a high entropy state. And this period, depending on how this transfer of energy happens, can leave signatures today in the form of relics, whether it be gravitational waves or extra radiation, or perhaps primordial black holes. And this is exciting to look forward to in the future. In terms of human timescales, of course, this history of the universe of 14 billion years, or this very short timescale of at the end of inflation, all of these are very far away from human timescales and human length scales. Right? We don't really play a role in any of this directly. This might seem, of course, sometimes depending on what I'm thinking when I wake up, it sometimes seems depressing. But that we are at no special place, we are no specific length scale or time scale that's relevant for the universe. However, this quote from Harrison, who was one of the people who understood the patterns of fluctuations in the CMB, or made some predictions about it, this quote is somewhat entertaining. That given that us humans, even though our length scales and time scales don't matter, we are part of the universe, and we are at least thinking about it at the moment, that we might perhaps be the universe's way of thinking about itself. So at least this is some scant consolation about what our place right now in the universe might be. Thanks a lot.
So thank you so much, dear Mustafa, for this excellent talk. And I have to say, I learned myself quite a lot. So now to the audience, you have two ways on asking questions. One is you can raise your hand. So please raise your hand and you will be unmuted and you can directly ask the question. Or you can write the question by writing, you can ask the question by writing it on the chat. So any question, please. So this means it was very clear, or or the opposite. But in my opinion, it was very clear. At least the people are enthusiastic. You have applause and thank you from William Wall and Mariam Al-Qualaf. But still no question. I have a question. What is the status of gravitational waves? You know, I mean, it's just because it's too tiny to be really detected, and it's so difficult that, you know, kind of you exclude this kind of theory, or why gravitational wave cannot play a role there?
You mean why? Sorry, to understand the question, why we cannot detect them, or why they cannot play a role during that period?
Yeah, I'm saying most why you can also not detect them, I guess, because they're too tiny, right?
Yeah. And so I think the thing is, right, so there is the gravitational waves that are produced from this period are high frequency because the size of the universe is very small at that time. So as a result of which the gravitational waves necessarily have a small wavelength, which means they're high frequency. Roughly speaking, you already know that you can't have too much energy density in these gravitational waves. Otherwise, they would have changed the universe at that time significantly, or at least we don't think it has. So the amplitude of these gravitational waves cannot be beyond a certain limit. Allowing these amplitudes to redshift all the way to today makes their amplitude about, I would say, based on current detectability technology, it's about 9 orders of magnitude away from what we can do at these high frequencies. So it makes it quite difficult to detect. At the same time, it's not that people haven't been thinking. There have been lots of people thinking about trying to build high frequency gravitational wave detectors to see if we can access this. It's just the sensitivity is not there. So I would say that it's not so much that we don't expect there to be gravitational waves. I would say that it's not so unreasonable to think that there will be gravitational waves from this early period. It's just that currently we haven't built detectors there. Astrophysical sources don't generate gravitational waves at this frequency. So initially there was no reason to build things there. But you want to build things where you're guaranteed sources. These are high frequencies where only early universe things do. But on the flip side of things, because that will mean that there'll be no astrophysical background there. So if you can build a detector there, it would give us pristine information about what's happening at that time. But currently, we don't have the technology yet.
So we have one raised hand. It's from William Wall. Willie, can you please unmute William?
Hello.
William.
Yeah. Can you hear me?
Yes.
Okay, great. Yeah, I really enjoyed your talk there. It's interesting stuff. I have sort of an ill-formed question, but it's based on some speculation I've heard before about people saying that, new universes are coming from black holes. Black holes represent like the new, a new kind of Big Bang happening somewhere. Because I found it rather interesting. You said that the surface of the black hole in the center of our galaxy has the same entropy as the cosmic microwave background. Would you care to speculate on that, or?
I know that you can talk about because we know so little about the interiors of black holes. We know what Einstein's theory tells us about the horizon to some extent, but we know very little about what's happening at the singularity in the middle, if there is a singularity or what is going on at that time. And there are solutions or there is at least thinking that these might be connected to other branches in the universe and so on. But in my opinion, this is quite speculative. I don't have anything more to add beyond what people say. This entropy argument, I think it's somewhat of a coincidence. I don't think if you take another black hole, the entropy will be different for that, right? Like it's just this particular black hole. I just chose this one because it has a similar number. And also, I wouldn't read too much into that at the moment, at least.
Okay, well, thank you.
So, there are some questions in the chat, Mauricio. Do you want me to look at those, or? I think, Mauricio, you are muted.
Sorry. Yeah, we have. Well, Don Ellis wanted to ask a question, but then he did not raise anymore his hand. But we have some question in the chat. One, I have to say, it's very generic, and I don't like it so much because we just have a name, and it's more, provocative questions, which of course we can ask. It's what do you think about the models? I don't know which kind of models. You are the expert, of course, that critique the inflationary theory. And you answer.
So I think I think it's a fair question. So inflation, in some ways, this idea of an exponential expansion giving rise to smoothing out the universe and giving rise to initial conditions for structure formation is consistent with observations. Right? So that's what we know. It doesn't mean necessarily that there are no other ideas out there that could also explain this. The benefit, in my view, the benefit that the inflationary theory has is that it is a theory where we can do the calculations and compare with observables reasonably well without worrying about quantum gravity too much, which we don't know much about. Other theories which have been worked on for a while, for example, theories with a big bounce, where the universe undergoes a crunch first and then expands out. It goes through a singularity, which we don't have too much control about what's going on at that time. So it's hard to make concrete predictions. Of course, people are trying, and it's worth making more effort in trying to understand that. So when people criticize inflationary theory, my answer typically ends up being that true, inflation, we don't have enough confidence in the theory that we should stop looking elsewhere. But at the moment, it's one of the few places where we have a calculable theory that we can make predictions and compare with observations.
Okay.
So that's why I think the status of that.
Now we have 3 more questions. Let's go through them. Is there a limit of how light the first light nuclei can be?
Well, because hydrogen is just protons, we know that's what we can have. So the light nuclei, I'm assuming by light you mean weight, but nuclei they're basically the mass of protons and neutrons together. So the lightest one you can have is hydrogen. After that, you can have helium. So those are the lightest ones you can form. And then you have the rest in the periodic table forming. You can't form, because of the way the universe is expanding at that time and the reaction rates that are there, it's very difficult to produce heavier elements in any significant amount at that time. So all the heavier elements or all the heavier nuclei basically are born in furnaces of stars and even heavier ones in cataclysmic events like supernova and so on. But only the early universe conditions only allow you to form light nuclei in the sense of hydrogen, helium, and trace amounts of lithium and so on.
Thank you. Then we have, let's go through the last 2 questions and then we will stop reading questions. So this is from Ellison. What actually is, so Andrew will say thank you. And so the Ellison question is, what actually starts the universe moving after the inflationary epoch? And then he's writing his mental picture is that post-inflation, the universe is suddenly humanly larger, but it is still stationary. Or is this just what we call the Big Bang? So so that you are searching for the cause of this sudden movement.
So it's a broad question, but it's an interesting one. And I'll interpret it at least as a question about what starts inflation, right? Like how does inflation begin in the first place? So for inflation to begin, you need a sufficiently large patch of the universe that's relatively homogeneous with a constant energy density, and then inflation can start in that region. How likely is something like that to happen, and whether we can get a patch of the universe like this at some point, is something that is an active area of research and is still ongoing. People debate how likely this is. So we don't know for sure, but it doesn't seem completely unreasonable that such a condition can arise in the universe. And the interesting thing about inflation is that once it starts, it just takes over, right? And so it just has to start somewhere. This question about what we think of so it could be a chance event somewhere where inflation just begins. The likelihood of that happening, we don't have a good way of, at least I don't have a good way of predicting how likely that is to happen from generic initial conditions. On the other hand, I would say that you said, is this a Big Bang? As I said at the beginning, people have different interpretations of what they mean by the Big Bang. It could be the initial singularity, it could be the beginning of inflation, or it could just be the hot dense state once the particles are already there. So it depends on what flavor you want, the Big Bang.
So last question from Mark Sargent. Why were the structure in the simulated regions at the end of inflation called solitons?
This is close to my heart in some ways, so I work on this a lot. So it turns out that solitons are, for people who don't know, solitons are localized configurations of the field that are exceptionally long-lived and stable. It turns out that in certain models of inflation, when inflation ends, the inflaton field itself breaks down into these localized clumps. And these localized clumps are exceptionally stable, at least for the timescales that are present at that time. So the nature of these clumps that form are solitonic, and that's why we call them solitons. They don't necessarily survive all the way to today. So they're not perfectly stable, but during that timescale, they're really long-lived. So that's why we call them solitons.
Okay. So thank you once more, dear Mustafa. Thank you again for having accepted our invitation to give your talk. You have a lot of thank you now still in the chat. And I would like to remind to the audience that the next Game Changer seminar on cosmology will be on October 6th, the latest from the CMB, and it will be given by Erminia Calabrese from Cardiff University in the UK. So we are very looking much forward to have again the audience back for this online Game Changer seminar on cosmology. Mustafa, thank you once more, and I think it's a day in Tucson, so enjoy your day. Bye.
Thanks, everyone. I appreciate it.